the school system. I graduated from the high school last year, and right now I'm a college freshman. So I'm not too far away from high school, I guess. And I'm here to talk to you guys about this area of math that I find very interesting. It's called graph theory. And I hope that you guys will also find it interesting. I hope to try to talk about why it's interesting to me and why we can use it in real life and such. So I like making my lectures very interactive. So I'll be first of all, if at any point I'm talking too fast or you want me to explain something over again, feel free to stop me. I'll be happy to do so. Yeah, if you have a question, also don't feel free to don't hold it in yourself. Just tell me whatever. And okay, let's get started. So I'm gonna start with just a quick overview of just math and then where graph theory falls into this, because there's a good chance because you're so young, or maybe you're very advanced, but if you're very young, you might have not heard the term graph theory before. And so when we talk about math, there's a lot of math that we learn in school. And well, first of all, we start out with the foundations, right? Like addition, subtraction, right? And so on, multiplication, division, and we go on. And why don't you guys tell me some of the topics you've been learning in school in math? Just throw them out, just yell them out, it's fine.
LCM and GCFs.
Okay, yeah, sure. Least common multiple, greatest common divisor, right? Anything else? Yeah? Any
Fractions.
Fractions, great. Keep going. Just say it.
Decimals.
Decimals. Okay.
Averages.
Yeah, average. Means. Okay. Great. So, all these things come from our foundations, right? Like addition, subtraction, multiplication, division, and so on. And we go through school, and we start learning these things, LCM, GCD, or GCF, fractions, decimals, averages, means, right? And there are formulas for all these things that are based on addition, subtraction, multiplication, division, and so on. And as you get older, you might be learning stuff like slope, right? And maybe, I'm sorry? Yeah, derivatives, wow, okay. Yes, at some point you get to derivatives in calculus. But before then, you have calculus, right? So before then you have algebra, right, and geometry and so on. Don't worry if you've never heard of these, some of these terms before, because this is stuff you don't usually get to until high school. But basically, I guess the rest of your math education from middle school, or from elementary school to middle school to high school, it will follow down this trend, right? You cover all these topics, and at the end of the day, you learn all of this, and yeah. So actually, I think something that I guess the school system never told me, or my teachers never told me, was that this is only about half of mathematics. So there's probably this other half that you probably have not heard of. This is what we usually call continuous mathematics. This is not really that official of a term, but I think if you look it up on Wikipedia, it'll be there. Not sure. But then there's this whole other side of math, which we call discrete math, that we don't really cover. And I think the reason why we don't cover it is just because it's different. And it doesn't all of these things, they have a logical sequence, right? So you learn addition, subtraction, multiplication, and so on, and then you learn fractions, and then decimals, and these things build on each other. That's the wonder of math, is that it builds on itself over and over again. But discrete math is kind of it's a lot of isolated topics that you don't really need all this background for, but you can go learn it on your own. And I find it very interesting because I find that this part of math, discrete math, so stuff you will find in here includes stuff group theory, graph theory, combinatorics, number theory, right, and so on. And what sets this group different from that group is that this group deals only with whole numbers, in that we don't really see fractions, decimals, these things. We like to, when we talk about discrete math, we like to think about things that we can count, right? So like a book, 2 books, 3 books. And that's why this part of math is actually lends itself to real world applications a lot, because these are things that like we can physically count. We can physically like count, right? Like you can use a lot of these things to like model like populations and stuff. Like you can't, like there's no such thing as like half a person, right? You can't say half a person does anything. Which is why discrete math is a good model for stuff like social networks and so on. And so I guess out of these topics of discrete math and more, my favorite is graph theory, and that's what I'm going to be talking to you guys about today. Okay, so let's start off with that. So here, can I erase this? Is this okay? Yeah, good. All right. It's not that important. Okay. So when I talk about a graph, what comes to your mind? Yeah, go ahead. Area, okay, that's fair. Yeah. Anything else? Go on. Yeah. William. Axes. Okay. Yeah. Axes, right? X, Y, right? And like lines and parabolas and stuff, right? You might have that, or like that, like functions, right, that you can plot. Like, or points, right? Like you have 0, 0, 1, 2. So this would be 0, 0. 1, this would be 1, 2, and so on, right? All of these, like stuff you can plot in like the Cartesian plane, like a plane, right? So that's not what I'm going to be talking about today. This is the type of graph that you're probably familiar with, and this is the type of graph that you learn in school a lot, right? This goes along like the whole continuous math thing, right? Because you can have points like 1.5, 2.7, right? The type of graphs that I'm going to be talking about are pretty different, but I guarantee that every single one of you have seen something like this before, the graphs that I'm talking about. And so the graphs, what a graph is in the discrete sense of the word, it's a collection of vertices, we call vertices, and edges. That's all it is. To give you an example of a graph, something like this. That would be a graph. It's just a collection of what we call vertices. So all these lettered things are vertices. A, B, C, D, E. And edges, which are the things between the vertices that connect them. Okay? And yeah, that's all a graph is. So at the moment, it might seem kind of abstract to you, right? Off in space. But you can actually use this idea of graph theory, it's like something as simple as just vertices and edges, to model a lot of things that we see in the real world. So like for example, let's talk about some examples of graphs. We have, for instance, so you guys know Milburn pretty well, right? You guys all grew up here, yeah. So, on Milburn, there's this road. You guys probably know it, right? Milburn Avenue. Yes. And Milburn Avenue has this like big intersection with another street, right? Main Street, right? Going down. Here's Main Street. Right, and like, let's say the middle school is like somewhere here, right? Am I right, or am I completely wrong? I think this is right. Is it or no?
It is.
I think it is, right?
It is.
Okay, and then the library, like
Oh,
we are
yeah.
here, right? We are here somewhere, right? We are here. Correct? Yeah, this is the library, right? Okay. And then you guys might also know that like over here there's another giant intersection with street called Morris Avenue, right? And I believe that if you go down Morris Avenue all the way, you eventually hit Main Street, right? It like curves, correct? Yes. So, I mean, what's the point of this? It just looks like a very poorly drawn map, maybe. But the point is that something like a road network, we call it like a road network because it's literally just roads. This is also a graph. Why? Because you have a bunch of intersections here. And you can model those intersections with vertices. And then this, like these roads would be equivalent to like drawing edges between them, right? And then, like these roads, there's distances attached to these, right? I don't know what the exact distances are, but like X amount of miles, some amount of miles, whatever. And then what a lot of GPSs do is they treat like these road networks as graphs, and they have like distances along these edges, and then they can run some algorithms on those graphs to try to find like the shortest path from one point to another, right, by the intersections. So that's an example of a graph. So that's one of the obvious examples. Something else? Might think of. Something else are social networks. Something like a social network, we can model like friendships. So like let's say you have William over here, right? He's a node. So basically, what? And then Sahil. This is how you spell your name, right?
Yeah.
Okay. Right? And they're friends, right? Yes?
Yeah.
Okay. So we can represent that with an edge. Okay? And then you might have some other friends. I don't know your other friends. But here, what's your name?
Nicole.
How do you spell that?
N-I-C-H-O-L-A-I.
N-I-C-H-O-L-A-I.
O-L-A-I.
Okay. So let's say you're friends with William. I don't know if you actually are. I hope you are. He's a nice guy, I think. And then you guys might also be friends. Let's say that there's this like the other guy, Bob, and Bob doesn't like Alice, so there's no edge between them, but then you guys are all friends, so you're happy. And then they're not friends, right? So social networks, this is a pretty simple depiction. Something that, I don't know if you guys are old enough for Facebooks. Probably not. Yes? No?
I don't think so.
No? But basically, like, how Facebook works is you create some profile, right? And then you have your own profile and you can friend people on Facebook, right? And then Facebook, the way they store this data of who's friends with who is they store it as in a graph form. So if two people are friends, they draw an edge between them. If they're not friends, there's no edge. So this has all been pretty simple so far, so I should probably actually get to the math. Okay, so this is just modeling. Other things you can model with just real quick, something like this. I'm sure you've all seen this before. This is also known as H2O, or water. It's also a graph. There's this whole field called chemical graph theory, where they try to integrate math and chemistry together York subway station. You can also see how that's a graph, kind of like the road map idea. Okay, so let's get to something a little bit more interesting. Also, sometimes I know my handwriting can be pretty bad, so like, if you need me to rewrite anything, let me know. Okay, so let me first give like a definition. We know what a graph is, we know what a vertex is, we know what an edge is. So we're gonna define the degree of a vertex. So what's the degree of the vertex? Well, this is easy. It's just the number of vertices, or sorry, number of edges the vertex touches. Okay. So for this vertex A in this example, it would just be 2. C would be 3, right? Touches 3 edges. D would be 2, and B would be 2. So the degree usually has some kind of significance in real world models. So for example, in like the Facebook example, a person's degree would be the number of friends they have, right? Okay. Now, let's try something. If we add up the degrees of this graph, what do we get? Well, let's say A has how many? A has how many? What was A's degree? 2, right? Oh, no, not this degree. Sorry, not this degree. This is not like, so the degree of, like, not like the angular degree. Like, that's not important in graph theory. That's like in an actual like geometry problem, you probably use like angle degree. Degree is just like, we just count like 1, 2, that's it. Okay, it's much simpler than like angles and stuff. So A would be 2, right? B would be 2, right? C be 3, D 2, and E 1. Okay. Now if we add these up, what do we get? 7, 9, 10. Cool. So this is the sum of degrees. Right. We get 10. Okay. Does anyone notice anything about the number 10 in this example? Yes?
It's like the number times 2.
What number?
Like
times
the
two?
A, B, C, D, E, like how many circles? Times 2.
In this example, yes, it happens to be. Okay, let's write down that information. So we have vertices. How many vertices do we have in this graph?
5.
Okay, how many edges?
5.
Okay. Let's draw another one. So this is one graph. I'm just like drawing the same thing. What am I doing? Okay, let's do that one. Let's put in another one, just for fun. Okay. Number of vertices? Sorry, am I blocking people? Like that. 5? Edges. Sorry. Oh, 8, right? Is it 8? Yeah, you guys just shout the answer, sorry. 8, sorry. I'm kind of slow at counting. Okay, now let's do the whole sum thing again. So let's do A, B. Actually, just to not be confusing, we'll call these different things. So let's call them F, G, H, I, J. Okay, so F, what's the degree of F? Shout out. 4. G.
2.
2. H. 3. I. 3. J.
4.
If we add these up, what do we get? 16. Does anyone notice anything now? Do you want to say this? Or Do you want to give an answer or no? Okay. Anyone else? Yeah, go ahead.
It's the number of edges times 2.
Number of edges times 2, yes, in both cases, right? Is that just like coincidence, or is this a special, or are these like special examples? Okay, let's try one more. This time, does someone want to come? Could I have a volunteer? Here we want to come up. All right, draw any graph. Just please don't make it too complicated, or else we'll be counting forever. Okay. Cool. Okay. This is 1, right?
Yeah.
Okay. Let's just really quickly do it. There's 4 vertices, right? 4 vertices. How many edges are there? 4 edges, right? Okay. The 4 edges. What's this degree? Well, the degree of vertex 1 is 3, right? Degree of vertex 2 is 2. Of 3 is 2. And 4 is 1. So we have 3 plus 1 is 4. Plus 2 is 8. Right. So we have 8. To some degree, is 8 again. So we have seemed to show, well, it seems like the case that the sum of degrees that we get every time is twice the number of edges. Anyone wants to give a hypothesis as to why that's the case? Yes?
On each edge, there's 2 endpoints, 1 on each side.
Right?
And for one endpoint, you count that line once. For the other endpoint, you count it once. So you count each edge twice.
Yeah, exactly, right? So basically what he was saying is, well, if we look at each edge has 2 vertices it's touching, right? So like let's look at this edge. It's touching B and D. When we go to count the number of edges that are touching B, we count this edge once, right? And then when we go to count the number of edges touching D, we count the edge again. So every edge is counted twice. And so that's the reason why the sum of degrees in any graph, in this case, happens to be twice the number of edges. Okay? Was that too slow by any chance? Do you guys want me to speed it up a bit, or keep going at this pace? What do you guys think? First of all, does anyone want me to explain that one more time or no?
You mean the number of degrees is half the number of edges. There are twice as many edges as, the number of edges is twice the number of degrees.
No, I'm saying that the sum of the degrees is twice the number of edges.
Yes.
Yes. Yeah.
Do you allow non-connected, isolated edges so that it would defeat this observation?
Isolated.
Like an outlier vertex 5 in Winston's graph that's not connected to anyone.
So like 5 right here?
Yeah.
Yeah. But notice that only changes the number of vertices. And it contributes 0 to the degree. So the number of edges in this entire thing stays the same, right? And the sum of degrees stays the same too. Right? So in any graph, this is the case.
So you have 5, do you have 5 vertices or do you count that 4?
This is 5 vertices.
Yeah. So,
Yes.
So 5 times 2, or should we do?
No, I'm saying the number of edges times 2.
Right.
So the edges is still 4 in this graph.
Yeah.
Yeah. Okay. All right, anyone want me to explain that one more time? Are we good? Yes? Should I go faster, slower? Yeah?
I don't get the vertices. Is that like the yeah, I don't really get that.
What vertices are?
Yeah.
Okay, so vertices are just these circles here. They represent like
That's
objects.
simple, okay.
Yeah. And edges are the things that connect.
Okay.
Okay, got it? All right. So any feedback on how fast I should go, or should I keep going at speed? Same speed? That's pretty good? Okay. Cool. Okay, sounds good. Let me just write what I showed you real quick. And this is what we call like the first theorem or fact of graph theory. It's like the first thing you learn when you learn graph theory. So write this fact that the sum of the degrees in any graph is twice the number of edges. Okay? All right, let's keep going. Let's see, how am I doing on time? 7:32, okay. Doing okay. All right, I'm gonna try something. Oh, I keep dropping this. Could I get 3 volunteers? You wanna go up? All right, sure. 1 more, or 2 more? Yes, yeah. Come. Nicola, right? What's your name? Hi, Alex, nice to meet you. Yeah, just take any marker. So I just draw your own graph, any graph, it can be any graph. Preferably, again, not too complicated. Okay, cool. Yes, yes. Okay, yeah. So, Sahil's right, Nikolai, no, Nikolai did that right. And this was Jordan? Jordan, yes, okay, cool. So now, we already know that in all of these graphs, the sum of the degrees is twice the number of edges, right? It's a fact, and we can think about that by counting. Okay, now let's count the number of vertices with odd degree in each of these graphs. Okay, so for example, in this graph, does M have an odd degree? This one. Yes?
Yeah.
Okay. So we'll just write it down. All right. You guys just list them out. Just list a vertex with odd degree. Yeah. P does connect to R.
Yeah.
Yes? Okay, cool. All right. Just shout them out. I'm sorry? O.
Oh.
Anything else? Or
Is it
no?
only for this graph? or-
Yeah, just this graph.
Okay.
Is that it?
Yeah.
Okay, cool. So we have, okay, never mind. Just leave it at that. All right, what about this one?
1,
Odd degree? 1? Yeah, 1 has
5,
3.
2,
5 has 3.
2,
2 has 3, correct? And 3 has 3. Yeah. So 4 only has 2, right? All right, what about this one?
1, B, D.
D, yes.
B.
B, yes. Anything else?
No.
No? Okay, cool. So I won't reveal the punchline just yet, but I want to try an activity. So as many of you as are willing, can you guys come around this area? Do a real quick activity. As many of you. Okay, that's pretty good. That's pretty good. All right, so, okay, so in the next 10 seconds, you guys randomly go around, and I want you to shake hands with whoever, okay? And remember, keep a running total in your head of how many people you shook hands with, okay? And for this to work, you have to remember that number. If you get that number wrong, then this will not work, okay? So just go around in the next 10 seconds, shake hands with as many people as you want. It can be just one person. You can just go sit back down if you don't like people. That's fine. Like it does not matter.
Can you shake the same person's hand twice?
That is okay. Yes.
Okay.
Yes, that should be fine, right? Oh, that's a good point. Yeah, no, that should be fine. Okay. So yeah, okay. Ready, set. Okay, so you're all at 0 right now. You're all at 0 right now. 10 seconds. Ready, set, go. You have to remember your number. Don't forget how many people you're shaking hands with. Alright, let's stop. Stop. Okay. Wait. Make sure. Alright, if you're counting that that handshake, make sure the other person also counting the handshake. Okay?
Okay, shake hands with yourself.
Alright, wait, to keep it simple, let's do that one more time. Let's say you can't shake hands with the same person twice. Because I have a feeling this might not go as well as I thought. Alright, ready? Alright, 3, 2, 1, go.
1, 2, 3, 4, 5.
Alright, let's stop. Alright. Okay. If you got an odd number, stay here. If you got even number, sit back down. This did not work. Someone messed up. Alright, let's do it one more time. Not everyone has to come back up, okay? Only if you want to. Alright. Make sure that if you count the handshake, the other person counts it too. Alright, ready, go.
1, 2, 3, 4, 5.
Alright, let's stop. Alright, you got even numbers, sit back there. You guys all got odd numbers? There's no way that happened.
I got 7 that I got. Oh, I got 7.
There's no way. Like math says that's not possible.
Did they shake with the same person more than once? Does that matter?
No, it does not matter. But this is not possible.
Why don't they 5 of them shake among them? So let's see how it works.
Okay, let's see if you took an extra one. Alright, so that was supposed to, okay. Number of, okay. Well, let's say there were 4 of you, okay, that got an odd number of handshakes. When there probably were 4 of you. Someone probably miscounted. But anyways, basically what just happened is graph theory. We can actually model what just happened with a graph. If you are each a, does anyone remember everyone they shook hands with by any chance or no?
No.
Okay. You do? Alright, cool. Jordan, you got a J. Who did you shake hands with?
I shook hands with him. Yeah, I did.
This is awkward.
Shook hands with you.
Alright. Jordan shook hands with how many people? 7? Cool. 7 people. So, whoever these people were, maybe they were you two, I don't know.
Not me.
Apparently we do not know. But these were some people in this room. And these people also shook hands with other people. They might have even shook hands with each other. We do not know. But basically, like this, you can see how this is graph. So we have vertices, you have edges, and so on. Now, what is the degree in, what is the significance of the degree in the graph? Should be pretty obvious. Like, what is the degree in this graph? It's the number of people you shook hands with, right? Right. So, okay. So apparently the number of people, the people who shook hands with an odd number of people are Jordan, what's your name?
Neil.
Neil? Okay.
Sean.
Sean.
Winston.
Winston. Okay. These 4 people. Now if we count the number, so these would actually be like the odd degrees in our graph, yes? Okay. Now if we count the number of odd degrees in this graph, we get 2. Right? In this graph, we get 4. In this graph, we get 2. In our handshaking graph, we get 4. Yes. Yes, that was what I was going for. They're all even numbers. So this leads us to another observation, which Winston, right? Winston? Okay. Which Winston pointed out, which is that it seems like that the number of odd degree vertices in any graph is an even number. Okay, let me just write that down real quick. This will actually form our second fact, so I'll just write that down. So, yes, sorry. Number of odd degree vertices in any graph is even, correct? Okay, why is this the case? Well, we had a lot of examples that show that this seems to be the case, but why is this the case? So this is the case. We can actually use our first fact to prove this. That's what happens a lot in math, or in discrete math, and so on. And in math in general, is that you use things that you've already learned to show things that you have yet to learn. So by this fact, we know that the sum of the degrees in any graph is twice the number of edges. If it's twice the number of edges, what kind of number is it? Yes? Yeah, it has to be even, right? Because it's 2 times the number of edges. So this, the sum of the degrees, this has to be an even number. Right, okay. Well, okay, so if we look at our graph of vertices, we can divide our vertices into 2 groups. We have our odd degree vertices, and we also have even degree vertices, correct? Okay. Now the odd degree vertices, let's say we take a look at all the odd degree vertices, and we add up all of their degrees, right? Then we get some number. So if we add up all the degrees of this, this will lead us to, what can we say? Okay, we can say that the sum of the degrees of the vertices is equal to the sum of the degrees of the odd degree vertices plus the sum of the degree of the even degree vertices. Is this correct? You guys all see that? Why that's true? Yes? Any questions? Okay. Right? What? So we're adding. Let's say we're adding up the sum. Let's say we're adding up all the degrees of the vertices. Right? We're trying to find this number, the sum of the degrees of the vertices. Well, for each vertex, we can either say it belongs in the odd degree group or the even degree group. Right? Yes? Okay. Cool. This we know is what? This is an even number, right? This is from fact 1. Yes? We know that the sum of the degrees of the vertices in any graph is an even number, correct? What about the sum of the degree of the even degree vertices? What kind of number is that? Yes?
It's also an even number.
Why?
Because any even number times any number is still an even number.
Are we multiplying them?
So the sum of any 2 even numbers.
Correct, yeah. So basically what William is saying is, here, we're just adding up a bunch of even numbers, right? We're adding up a bunch of even numbers. If you add up a bunch of even numbers, like 2 plus 4 plus 8 and so on, you get, what, another even number, correct? So this has to be even. You guys see that? why this has to be even? Right, because these are the degrees of the even degree vertices. Yes? Okay. So we know this is even, and we know that's even. So what does that have to be? Even, right? Right? Because if you add, there's no way you can add an odd number to an even number and get an even number.
Because if you multiply and the number by 2 and the odd number will still get a
Yes, that's true. That's true. Yes, that's how we get this over here. Yep, you're right. So this has to be an even number. Yes? Does anyone want me to repeat why that's the case? Or you guys get it? Get it? So this has to be even because basically you can think of it as, let's say this was like some variable x, and you were solving for x, and you took, basically to solve for x, you would take this even number, you subtract that even number. You would have to be left with an even number. Yes? All right, so the sum of degrees of the odd degree vertices is even. What does that say about the number of odd degree vertices is what we want here? Yes?
It also has to be even.
Why?
Because only the sum of an even number of odd numbers is going to be even.
Yes, correct. So this immediately implies this. And why? Because here, what we're doing when we calculate this value is we're adding up a bunch of odd numbers, right? A bunch of odd numbers. So you might have like 1 plus 3 plus 5 plus 7, or why am I doing this? Plus 3 plus 1 plus 7, and 1, 2, 3, 4, 5, 6, yes, plus 7 and so on, okay? And we get some number. And we know that this number has to be even, right? This number has to be even, because we showed that from this, and that, this has to be even, right? So if this is even, if the sum has to be even, then we have to have an even number of these. Yes? Because if we had an odd number, like let's say 1 plus 3 plus 5, that's three numbers, right? We get an odd number, which we know is wrong. Yeah, so this has to be even. Okay, does anyone want me to repeat that? I know it's kind of convoluted. Anyone want me to repeat any part of that argument? No? All right, cool. So that's how we show the number of odd degree vertices in any graph is even. Now, this might not seem like that big of a deal. But like, I feel like it's kind of interesting because if you think about graphs and what they can do, we can use them to model basically almost any kind of relationship network, right? So what can we say? Well, we can say that the number of people who just shook hands, the number of people who shook hands with an odd number of people, that number is even. We can say that. What else can we say? Well, we can say that in the history of the world, we can model the history, like in the history of the world, if we look at the graph of people who've ever shaken hands with anyone, right? We can draw that as a graph, yes, right? Each person is a vertex. If you ever shook hands with someone, then that becomes an edge. So the number of people who've ever in the history of mankind ever shaken hands with an odd number of people, that number is even. You can say that. If we bring this to like the Facebook example, Facebook, we said what? The degree is like the number of friends you have, right? So the number of people in the world who've ever had an odd number of friends, that number is even. You can say that for sure. Yes. And I think like, and it will remain the case like to the end of time. Like you can keep friending people. You can try to like, friend people randomly to try to like disprove this fact, but it won't work because that number will always be even. So yeah, I thought that was pretty cool. So that's your first 2 facts of graph theory. Let's see how I'm doing on time. 10 minutes left? Yes. Okay. Okay, let's keep going. Can I erase this? You guys good? Yes. So I'm going to write another definition for you guys. Definition. In this definition, we're going to define a special kind of graph. It's called a planar graph. planar graph is a graph that is connected, that is completely connected. So completely connected means that there's no like random vertices like off by themselves, or there's no like two distinct parts of the graph that aren't connected by edges, right? Everything is connected, completely connected. And the edges do not cross. What does that mean? Edges do not cross. That means that if we were to draw a graph, this is a planar graph. This is a planar graph. Okay. Let's say we were to draw another edge right here. The edges cross on this paper, so this is not a planar graph. Okay. And we can fix this by saying this is the same thing as if we had this, and what we want the edge to go this way, right? But instead, if we draw it like that, that's a planar graph. Okay. And why are planar graphs useful? Well, planar graphs are kind of still the same thing. So like, if we talk about like road networks, you'll never get a non-planar graph that's like on the street. Like two roads will not like just cross one another without going through a point. There has to be like a point where they cross. Like in a like if you think about like let's say like a map of like the U.S. or something, right? And oh shoot, I'm so bad at drawing. I don't want to draw the U.S. If you have like a picture a map of the U.S. and let's say that like all the states are like a vertex, and if they border one another, then you draw an edge between them, right? Right. That has to be a planar graph, because you can't have like two edges that just randomly cross. Yeah. Yes.
How about a bridge?
Bridge. Like, what do you mean?
It's like there's one road going this way, then there's like a bridge on top of the other, on top of it.
And
Bridge connecting two.
Yeah.
oh, like a
that.
bridge going
Yeah.
over.
Yeah.
Yeah, I guess you could say that that's an example, but I guess like usually like you can, I don't know, I like usually you could get off of that bridge somehow and get onto the other road. I don't know. Like, anyways, for simple purposes, planar graphs are actually a pretty good model for the real world. And let's see. Okay, I have 5 minutes left. So here, I want to show you guys some pretty cool examples. So I guess I'll just go straight into it. I guess I could write this as like a third fact. So this is something that if we had more time, we can explore on our own. I would get you guys, a bunch of you guys up here to draw a bunch of graphs, and we would show that this is true. But basically what was proven by this very famous mathematician called Leonard Euler, he proved that, and you will find him in like a lot of other places too as you learn more math and stuff. But he proved that, so if we define, okay, so let me just define one more thing. Bases. Okay, so we know what vertices are, yes? We know what edges are. Now we're going to define this thing called like a face. So what a face is just like in a planar graph, it's like this section that is cut out. So this would be like a face. If we were to number the faces, it would be like that's a face. This triangle here, that's also a face. This is a face, right? And it's enclosed. And then this giant thing on the outside is also a face. Does that make sense? It's just the space in between the vertices and edges. Okay. In non-planar graphs, you can't do this because there's no definite the faces have to be bounded by the vertices. So in this example, vertices, we have 4 of them. Edges, we have 6 of them, and faces, we have 4 of them. Correct? Yes. All right. Let's do one more. Okay. here we only have two faces, you see that? Because there's this giant one on the outside, and then there's like that one, like that, right? So vertices here, we have 3. Edges, we have 3, right? 1, 2, 3. And faces, we have 2. Yes. All right, so basically what Leonard Euler proved was that in any graph, or sorry, in any planar graph, I should add, because this doesn't make sense for non-planar graphs, but in any planar graph, we have this formula, which is the number of vertices minus the number of edges plus the number of faces will always give you 2. And this will work for any planar graph. So like vertices, you can see here, it's like, in this one you get 3, right, vertices, minus 3, number of edges, plus a face. This gives you 2. In this planar graph, you have 4 minus 6 plus 4 equals 2. Okay? And this fact will be true for any planar graph. And so like, we can draw a bunch of graphs on the board, and it will probably be like, you can probably see that this is true for yourself. But where this fact really comes, I think, is like its most powerful form is when we look at the real world. And I brought a bunch of objects here to show you guys how this applies. So here we have like a